inside the previous lecture, we created our trend following strategy. But one thing we will know by now is that there were a lot of repeated code. So things like the PNL computation logic and the allocation of the instantiation of some of the variables are very repetitive, and we want to do that in an object-oriented manner. So we're not going to go too much into detail about object-oriented programming, but if you're interested, it seems to me that this course should give you a lot of the basics that you need. We're just going to go through some key examples so that you can just follow along. So we just create a test file. Okay, inside here, let's say we do something like class of animal, right? And in order to say that a monkey is an instance of an animal, we will pass in that to the class parameter. So this says that monkey extends animal, and the relationship is said to be a relationship. So monkey is an animal. It's an animal. Okay. Now, what this does is, if we do something like name, and we do say my name, then it will say my name is something. So we can actually create an instance of a monkey. So let's say we do this. Right? Then we say we create an instance of monkey, and we'll pass in the name equals to monk, and we'll do monkey.sayMyName. So what this will do, we have to instantiate. So the name equals to name. So let's try this out. This will inherit this particular function. So this is good, but the thing we want to demonstrate from this is what is known as function overriding, as well as function overloading. We're going to focus on function overriding. So a function overriding means that we redefine the base class function in its derived class with the same signature. So this means that this will have the same function signature. The function signature is, well, the function name as well as the parameters. And if we do this, interestingly enough, we will not actually access this particular function. We can, of course, say that we want to explicitly call this using what is known as a super. So super will refer to the parents methods. So if we do super.sayMyName, right, then we will go into this parents methods, and then we call this. So we'll print this, and then we will call this. So we'll get both the print statements. So in terms of let's say we have ape instead. Okay, we can further extend class monkey is an instance of an ape, and then we will take in the same function parameters. You can of course take in other things like species, and then we have the species equal to species. And if we do this, we will we need to specify species. I don't know what kind of species there are. I'm just gonna put in a random monkey thing. I don't know. And this will, okay, let's say we stop calling this. We comment this out. We'll actually just call this function only and not this. So in terms of what ends up being called, we need to look at a object inheritance diagram. Okay, so suppose we have the animal class, and then we have the ape class and the monkey class. And each of these are parent shell extensions. So this will extend, this will extend. So a monkey is an ape as well as an animal. So when we call a method, say my name, what it will first do is it will check. So we say monkey is equals to an instance of monkey, right? So this object here, so monkey.say my name, will first check in the most specific class instance. Okay, so here we have say my name, and in this case, if the function say my name is implemented inside the monkey class, then we will call this function. Of course, we can, if there's no such function, then it will go up this inheritance ladder, and then it will see if there is an ape say my name implementation, and then it will try to call that. If ape also does not have this implementation, then it will go up to animal, and if animal does not have implementation, then we will throw an exception. So I hope that kind of makes it clear what an inheritance diagram does. Now in our case, we're not going to go too much into detail, but it's very useful to know these concepts in object-oriented programming, because that's what we are going to be discovering. Anyhow, we are going to save this as set2 so that you can follow along. Compress and put this as set2, and we will upload this into the lectures. Anyway, let's sort of rename this as alpha1. Okay, and then let's rename this as alpha2, and rename it as alpha3. Okay. And let's create these two different files again. These three different files again. So what we want to do is we want to use this utility alpha class, and we don't want to be repeating code. So let's go into this, put that here, and we're going to do something. We're going to extend the parent class. So every alpha1, alpha2, and alpha3 are all instances of the alpha object. So let's do from utils import alpha, right? So we're going to get a class alpha1 is an instance of the alpha object, okay? And immediately this alpha1 class has access to all of these particular functions, right? But we saw that there are a lot of there are differences when it comes to this function, and there were some differences when it comes to this component inside the logic. So if we saw for alpha1 that some of the computation was done here, then we will do some instrument computation, and then after the whole thing we will do the cross-sectional computation. So it is not that straightforward to see how to generalize this particular function, but we could try, of course. So how will we proceed? What we're going to do is we're going to say that inside this utility function, we want to do some pre-computation. So pre-compute, trade range, and then we also want to have some post-compute. So now we say that, okay, there will be some operations that is done after we join the indices, and there will be some operations to do before and after we do the indices. So we're going to separate these two pieces of code logic, and we're going to just leave this as is. Then now we have to, of course, implement these two functions, so self, trade range, but these are not going to be concrete functions. So these functions are not going to be implemented because in some scenarios, as you saw, there will be no post computation. Whereas in this case, you see there are two for loops, right? So one for loop here, one for loop here. So this is the pre-computation, and then there's post-computation. But in this case, there's only one for loop, so it'll skip the double computations. Okay. And the rest of these are pretty standard, right? So actually, one of the things we want to say before we go on is we're taking this ticker dfs and we are going to possibly pass it through multiple alpha. alpha object. So for example, if we do this, then if alpha2 modifies, so if we do something like alpha2 to run simulation, right, then it's inside the alpha2, we are modifying this TF object. So this TF that we pass into alpha2 may not be the one that we pass into alpha3, and that is a problem, right? Because yes, we assume that this is immutable, but after we pass through this run simulation, then this data file is going to be different. So in order to prevent like minor errors like that from happening, we're just going to do from deep copy, import copy, import deep copy. We're going to do this, and this just means that we're going to refresh. We're going to create a new copy of the data file so that we do not change the original data copy. Okay, so everything here is pretty standard, but let's just remove this print statement. And this will be different for different strategies, which means we also need a generalization. Actually, we can kind of generalize it already. So we have some forecasts, and then we have a number of chips that we want to bet. And let's call this compute signal distribution, right? So eligibles and date. And let's say we delete all of these, okay? So we can sort of just simplify this to forecast instrument, and then we will divide this by the total number of chips, and everything else will stay the same. So this is a more general function. But of course, then we are expected to implement this now, right? So we're passing eligibles and the date, and we are expected to implement this inside the particular concrete instance of the object. So if strategy 1, we want to implement the forecast computation inside here, inside this function. Remember that we said that we did this. We said that it will go from the bottom up. So if we have an alpha class like this, and then we have compute signal distribution, and then inside this is an empty implementation, and a concrete object and a child class extends that, and in this case there is some actual legitimate computations of the score, right? So dot dot dot, and you return this on forecast. Then when we call alpha dot compute signal distribution, it will start from the bottom and it will go into this, and if this is implemented, it will return the forecast, and it will not go into this empty implementation. So actually we can enforce this empty, we can enforce the implementation in the child class by creating an exception, right? So we can say class abstract implementation exception, and let this be an exception. So this is an instance of an exception, which means we can raise this, right? No concrete implementation for signal generation. So, okay. So imagine inside the alpha class. Okay, let's go to alpha 1. Okay, let's go inside the main file. Let's do from alpha 1, we do alpha 1.run simulation. Okay, let's ignore everything here below, and let's see what happens. Okay, we want to run the main file. So there's no implementation inside, so this is just basically same as running the plain alpha file. But what you will come across is that there is no signal distribution being implemented, so you get an error. So what you want to do is basically implement these 3 functionalities here concretely, and this will give us the full strategy. So I hope you get what happens, right? So if I go inside here and I say alpha 1.run simulation, this alpha 1 does not implement this run simulation method, so it will travel up to the alpha class. Then it will go to alpha 1, then it will go to alpha to run simulation, and then it will compute the meta info, and then it will say pre-compute. Then we'll start from the bottom of the object inheritance ladder, and we will search for this method. We will run this method, followed by this code, and then we'll say post-compute, and then we will try to look for this code. And then we would continue down here, and every day we would go compute signal distribution. And we would go from the bottom and run this code. It should never reach here because that means the signal forecast is not implemented. So you should always implement this method, okay, which should return forecast and forecast chips. So I'm just going to say, okay, that's 0 and 0, right, and the return forecast. Yeah. And this should basically give us access to the full logic. And as long as for each alpha strategy, we implement these 3 functions. You don't even have to implement these 2 functions, really. These are optional. The only one that we enforce was this method, because otherwise it would raise an exception. But what we have to do is essentially compute this thing. So let's compare it to this over here and see exactly how to implement this pre and post compute. Okay, so inside the pre-compute, well, we're going to do it for instant instruments. Let's just copy and paste this. So, okay, we don't need this data frame anymore. And so let's do self.outForce equals to this, and then you can append self.outForce and equals to alt4. So we're going to save inside this dictionary. It will inherit the parent method, but okay, you don't have to write this, but it's nice to do it. It's nice to do this, so we can just follow along. So just do this, and all this is optional, but inside the pre-computation, we're essentially doing this logic. And inside the parent class, so okay, after we finish this logic, we're just going to return, and then we'll let the control flow go back to this piece of code logic after the pre-compute, right? And then we will do the rest of the computation inside the post-compute. So what do we do inside the post-compute? Okay. So here we have, let's create a temporary array, and let's do inst. We want to do this line, so self.inst for. So this is where we do the alignment. So this is where we do the alignment. Okay, and then we do this line over here. So have this. Okay, and then we can do this logic. Right, so okay, let's import pandas. Import numpy. We do this here, which is very nice. Okay, and this is precisely doing the same as this. So okay, if you look at the original alpha class, it would do this inside the pre-compute. Then this will happen inside the main. This will happen inside this, and this will happen inside the main logic. And then afterwards, we'll do a post-compute, which is equivalent to this and these 2 statements, which is written inside here. So you should you can just use print statements to really track where the code is going, but it shouldn't be too difficult to understand the flow of the logic, right? So this together with this is exactly the whole thing. So if that makes sense, we can move on. Now we have to implement this and this logic inside of this compute signal distribution. So okay, again, nothing complicated. Suppose we can just do this, right? We can just copy and paste. And then we had forecast equal to this, or inst individuals forecast inst is equal to 1 if based on this logic. And then the total number of chips will just be the sum of the absolute values of forecast values. Okay. So this 50 lines of code should be doing the same thing as this 150 lines of code. And we managed to skip all of the PNL computation and things like that. Right? We managed to skip all of this lines of code. And let's see whether our implementation is accurate. So we can access the old alpha. So import alpha 1, alpha 1, alpha 1. So okay. So this would actually be the new alpha implementation, and this would be the old alpha implementation. So let's see if the two results are similar. If they're similar, then we have made no errors in implementation. So that's good. Right. Yeah, I think everything here is good. Let's try it out. So compute8 main pi. Super object is no attribute. I need to do this. Okay, so you see that the first data frame and the second data frame are identical. So they're doing the same computations. And our code for the first, for the later implementation, is about half of the second implementation, of the earlier implementation, sorry. So this is a much better way to do this, right? Again, you think that this little power to doing it in this way. Now suppose you have 100 alphas, right? And they're all running in your portfolio. Now, if you change a little bit of implementation, like let's say you always want to be twice leveraged, then you will do this, right? Then you will end up having to go into every single alpha class. Now, for example, if you do this, every instance of the alpha object will instantly adopt a twice leveraged portfolio allocation. On the other hand, if you have this kinds of implementation where it's not extending any parent class, then you will have to go into each of the 100 files and do this, and it will be a very painful experience. So that was our first class implementation. Now, we will go ahead and implement that same logic for the other two classes. So let's go to alpha 2, and these other two will be fairly simpler compared to the first two. So okay, let's go to the alpha 1 class, and we want to do this. So it's like here. Let's close the other class, and we want to do the implementations for this. Okay, so we'll do the implementations for this. Actually, if you realize inside the alpha 2 class, there's not a lot of post compute, right? So we'll just do this. So this is fairly easy. And then do self the alphas is equal to alpha, and then we return